Hi folks, I guess we are live. Let me just check the sanity of the connection, what the stream quality is and all that before I jump into the discussion itself. I guess we are live, right? So just let me know in the chat window if you can hear me. Uh, yeah, so just let me know in the chat window if everything is working properly or not. So yeah, can everybody confirm if everything is working as expected in the chat window? Because I see the stream quality to be perfectly all right on my own box. So please do let me know. So okay, sounds good. Thank you, folks. You can hear me. Things are looking good. Yes, okay, that's good to know. So since I'm a little early, as usual, I'll spend some time. Hey, folks, very good morning. Thanks for joining in. Anyway, it's a lockdown, so yeah, so it's easy to join in at this point of time. Yeah, it's working fine. Thank you, folks. Thanks for the confirmation. So let's do one thing. We'll start the live session itself at 10:05, right? 5 minutes past 10 o'clock. Till that time, I'll try to answer a few questions. But before we jump in, very importantly, I'm doing this live from my home. So if there is any power cut in between, of course, I'll lose my internet connection and I can't control those parameters. At our office, we have a backup and all that ecosystem. Here, while there is a backup, it takes a few minutes to kick in. So if there is a power cut, please be patient. I will try to join back in the same live session or will create a new live session. If the old live session dies on YouTube, I'll immediately create a new live session and continue the discussion there, right? So I want to repeat it for the benefit of everyone. In case there is a power cut at my home, it takes a few minutes for the generator to kick in. In the meantime, you will not be able to see the live because my internet connection would be down. Number one. Number two, in such an instance, please be patient. I will try to join back in the same live session, or in the worst case, I will try to join in a new live session that I create if YouTube kills the previous live session. Just wanted to make that clear, right? So good. Okay, so with that out of the way, so please be patient if something goes crazy wrong. Okay, so I saw a very interesting question. So let me tackle that right away. So one of the questions asked, what will be the job opportunities during a pandemic, and we don't know if there is a recession after the pandemic and things like that. It's a very valid concern, right? I'll tell you my own personal experience here. I graduated at the peak of recession. I mean, I was the recession batch, literally. When I graduated, it was the peak of recession, and it was crazy, let's be honest. And that was considered the greatest recession ever after probably the Great Depression in the US in the 1930s. So, and anyway, most IT jobs are dependent on Europe, US, and other markets. Of course, there is a small domestic market for IT and product-based companies in India, like companies like Flipkart, etc. But that's smaller as compared to other multinational companies. So in a recession, let's be realistic. We don't know if there is a recession. Let me make that clear. We still don't know if there is a recession because technically recession requires 2 quarters of GDP slide, right? So we don't know if there is a recession in China. We don't know if there is a recession in India. We don't know if there is a recession in the US or in Europe. We still don't know. We'll have to wait for a few months, 3 to 6 months, to really know the financial and the economic impact of the coronavirus spread. And again, if there is a new drug or medicine or a vaccine that is created fast, surely the impact will be lesser. If these lockdowns continue longer, certainly the economic impact will be more. Thankfully, many countries like India, Germany, Canada, US, they all have launched financial packages so that companies don't go under, businesses and individuals don't have to file for bankruptcy. Thankfully, there is a very swift action taken by governments all across the world, including China, in terms of announcing financial packages to avoid a deep recession. So let's be hopeful, let's be optimistic that this is a short-term thing. During this short-term thing, so let me talk about the immediate 3 months. The interviews that have already been scheduled, so for some of our students, they're being conducted via Skype and other channels, right? The interviews that are not yet scheduled, because there is no way you can go to an office and give an interview at this point of the lockdown, some of those have been postponed, right? So during the pandemic or during this, whatever, We don't know how long this will also stay. At least officially, the lockdown is till April 15th. We don't know if, just give me a second, let me adjust the light. Okay. So we don't know how long this will stay, but during the lockdown, expect reduction in interview calls. Because the HR is sitting at their home, the interviewers are somewhere else. It's very hard to coordinate all of this, and certainly getting the basic work done is the top priority right now, and not hiring as right away. Of course, if there are interview loops, again, we have some students whose interview loops already started. Those are being completed and the decision would be given to them as soon as possible. All the interviews are being conducted over Skype or some video conferencing tool. Number one. Number two, new job postings have reduced. We have already observed it. We are already in touch with all of our recruiting partners at various companies. And they've mentioned that once the lockdown is over, their recruiting process will re-begin. Right? So my suggestion during the lockdown period is to become better programmers, better software engineers, better machine learning engineers, better data scientists. That's what I would strongly recommend. Number one. This is the immediate 3 months. Let's take the worst case. Imagine there is a recession. Because we have to be prepared for worst case. Again, we have to be optimistic about life, but we also have to be realistic to prepare for the worst case scenarios. Again, this comes from my own personal experience. I was the recession batch. In the last 2008-2009 recession, I graduated at the peak of recession. Right? So in recession, what happens is this. There will surely be fewer jobs. Let's not forget that fact. During the recession could last, we don't know how long it will last, but thankfully, since most governments have put out financial packages, the recession, even if it is there, hopefully will be short. Now, if it is short, no issues, because the market will again kick back in, the jobs will kick back in. But even in the peak of recession, there will be jobs, because companies want to always innovate. There are a lot of companies which are sitting on piles of cash, and during recession, it is the best time to create competitive advantages. Of course, there are some companies which are not managed well, which are sitting in loads of debt, which have just raised venture capital money left and right. They're not profitable. Those companies will have a hard time recruiting. But companies which are well managed with good balance sheets, they have financial resources, and they tend to invest more in the future. Because during the recession, right? During the recession, there will be fewer jobs, no doubts about it. But the better prepared people will surely get jobs. That's something that I'm not at all worried about. If you prepare well, if you work hard, even during the recession, you can get jobs. The best part is post-recession. Okay, that's when, let's assume the recession, worst case, all these are assumptions, okay? So let's assume the recession lasts 4 or 6 quarters. After the recession, there will be a financial upswing. Again, you can look at stock markets, you can look at job markets, you can look at anything post the 2009 recession. After the US government bailed out the major banks, the upswing is enormous. And I have seen that upswing myself in my career. And if you're well prepared, again, during the recession, or if you lose a job, again, some of you may lose your job. Let's be realistic about it, right? Some of you may lose your jobs. Your objective should be to prepare to learn for the post-recession world. Again, during the recession, you may have some hardship. But after the recession, no governments, no financial institutions will tolerate too long a recession. Okay, today we understand macroeconomics well enough that we know how to get out of a recession. We got out of the Great Recession in 2008-2009. So we are much better prepared now, because we have seen it just 12 years back, exactly 12 years back. So we know how to deal with it, and I'm sure there are a lot of macroeconomists who know how to deal with it. Thankfully, governments also will listen to them. So post-recession, there will be a huge upswing in jobs, right? So what you have, again, I have seen this. My own career took off post-recession with the whole growth which started from 2012 onwards, 2011, 2012, say, whatever growth happened, lot of machine learning careers, lot of software engineering careers took off in that post-recession world. Because the recession peak was in 2009, the recession almost ended somewhere around 2010. 2011 se things started taking off. So what you need to prepare for is, if the recession is for 4 or 6 quarters, you need to plan for how your career will take off post the recession. There is nothing to panic. Of course, you have to be careful with your finances to some extent. You have to, you should not spend on crazy things. you should spend on improving your skills. You should spend time, energy, resources on improving your skill set for the post-recession. Once everything goes out, you have to be prepared for the job market, for the opportunities that come then. Again, recession or the pandemics are something that are not in our control, right? So the only thing that we can do as responsible citizens is to stay and follow the guidelines of various governments and government organizations to stay safe and not to spread the disease. That's all we can do. While doing that, the other thing that we can do is to actually continuously improve ourselves to better prepare. Again, how long the recession will be, will there even be a recession? We don't know answers to all of that. That will take a few months to pan out, and hopefully even if we get into a recession, a few quarters to get out of it. But during this downturn is a great opportunity for you to prepare for the post-recession growth. If you panic, if you go down, if you go into a depression, you're only hurting yourself and your long-term career. Again, it's very human to panic, but take a step back and say, what can I do now for a better future for myself and for everyone? That's a question you have to ask yourself. Again, this is something that we as a company are also thinking very deeply, right? Because we want all of our students to succeed, right? So please understand these realities of life. If pandemic is short term, I'm hoping it'll be just a few weeks. But post-pandemic, if there is a recession, even that hopefully will be short, because there's a lot of infusion of money into financial markets and financial institutions, and of course, individuals, consumers, etc. across the world. So hopefully even that hit will be small, even if it is 4 or maybe 6 quarters, worst case, right? Prepare for the world after that. That's my key suggestion to everyone. It's very common to have this concern. Please don't panic. Please don't go into a very negative mindset. You have to be optimistic about the future, but also realistic and hardworking enough to prepare for that future, right? Again, I've been through this once. I know it very, very, very well. I've been through this journey once. Thankfully, I'm old enough that this is my second big hit. So hopefully, last time we got out of it. I'm very sure this time with much better and swifter action, even if there is a problem, we'll get out of it thanks to governments and macroeconomists, right? So, okay, sounds good, folks. Let's dive into the discussion itself. I knew that this was one of the top questions on many people's mind, and some of you have asked me at the very start of the live session itself, so I thought I'll cover it. Again, a quick data point here. Please understand that if there is a power cut, because I'm doing all of this from my home and not from office because I can't go to my office now. If there is a power cut, please be patient. I'll try to rejoin the same live session. In case Google or YouTube terminates that live session, I'll try to create a new live session as soon as my generator kicks in, and I'll join within 5 to 10 minutes. Please be patient. We'll try to complete the overview session today. Okay, sounds good. Again, one more thing, because we want our students to be better prepared post the pandemic, and if there is a recession, post the recession. That's why we have started these live sessions wherein we want our students to improve their programming skills. I think we did this announcement yesterday. So again, we'll do some of these live sessions open, probably the early live sessions. We'll do them open to everyone so that everyone can benefit. The more complex ones which require our course content, we'll do it only for our registered students. Okay, sounds good. So sounds good. So let me go into the screen share mode and start with the live session itself. Okay. So I hope all of you have seen the announcement video. This cannot be a dive deep session. I can't cover whole of AI in 2 hours. I hope everybody can see the screen. I hope everybody can see the screen. Let me just refresh this. Okay, so can you people confirm if you can see my screen and not my face now? Just wanted to make sure that my screen is shared, because I'll be writing a lot of stuff there. Right, so can you see my screen? Can you guys see my screen? I'm hoping it is so. Just confirm, please. Okay, this looks good. So let's dive into the discussion itself. Let me also look at my streaming tool. Yes, it is streaming the live session slides. Again, I've drawn some diagrams just in the interest of time so that we can cover more things faster. Okay, the first and foremost, this live session is an overview of AI algorithms. It's a 10,000 feet view. It is not a dive deep. Let me also make that very clear with this. What is the objective and agenda? It is to give a broad overview of people who are planning to learn machine learning or who have learned some machine learning. I wanted to connect all the big dots so that you have a context of what's happening. Again, I'll try to do this using I'll try to use a simple toy example or a real world example so that you get better perspective of the problem. And simple overviews of techniques. Again, please understand that it is not a dive deep. I will not, somebody was asking me about interview questions. Unfortunately, we can't cover it in a 2-hour live session. Probably we can do one more live session. Even interview questions, I don't think we can do more than 20 interview questions in a 2-hour live session because I have to explain answers also, right? So in the interest of everyone, this is a broad overview. Let's go into it. Again, I'll try to simplify it as much as possible. I'm assuming that you don't have any background. My biggest assumption is that this is a broad overview for people who don't know anything, who have just heard about AI or machine learning, who wants to get a big broad overview. Okay, so I'm not assuming any prerequisites here, right? So first and foremost, so in my announcement, I also mentioned that there are multiple parts of machine learning and AI, right? So just a second. Okay, so there are multiple parts of AI. So first and foremost is data analysis. Okay, this is all about, again, data analysis uses lots of mathematical techniques. I'll cover some of them briefly, give you an intuitive understanding of how they work. So data analysis is one big area of AI. The second is classification techniques, right? So again, this is something that I mentioned in the announcement video also. Then you have regression techniques. Then you have clustering techniques. Then you have mostly deep learning techniques. Again, within deep learning, there are multiple sub-techniques that we'll discuss about. And there is reinforcement learning, right? So these are again, this is not the only way to think of AI. There are many ways of looking at AI, but this is one way, this is one broad picture of looking at AI, right? So this is the picture that we will try to go. Again, we are starting with AI. Within AI, there is data analysis. Within data analysis, I'll cover a few key aspects. Within classification, I'll try to cover a few algorithms with simple diagrams so that you understand what's happening. Within regression, I'll cover a couple of techniques. Within clustering, I'll cover a couple. Within deep learning, I'll try to cover more techniques. Within reinforcement learning, I'll try to give you an overview of what reinforcement learning is, right? So I hope this is clear. So let's start with data analysis itself. Again, within data analysis, one of the very important topics for data analysis is plotting of data. Again, as high schoolers in our high school days, 8th, 9th grade, probably even 7th grade in some boards or in some syllabus, we've all learned about plotting. What is plotting? So let's take a very simple example. This is a running problem that I'll use throughout this live session. So imagine if given a patient, we want to determine if the patient is diabetic or not. So is diabetic is what we want to predict. Okay, let's assume we want to predict given a patient if he or she is diabetic or not. Now to understand that, let's assume I am given two variables. So please, again, I'm using some terms here. I'm given two variables or features, right? So let's assume I'm given two variables or features for each patient. I'll represent a patient with X, right? So for each patient X, I'm given two variables. Let's say I'm given weight and height, right? So I have multiple patients. Some patients are diabetic, some patients are not diabetic. Okay, let's assume I want to visualize this data. Because remember, humans are brilliant at recognizing visual patterns. We are terrific actually, right? Humans are very, very visual creators. Since the time you were like 6-7 months old baby, you have been recognizing visual patterns like the faces of your parents and things like that. So we are very good at visual patterns. And plotting is one way of representing data that you have into visual systems so that you can better interpret it. It's as simple as that. So let's look at this plot. In this plot, for every patient here is represented using an X, right? So every patient here is represented using this cross, right? For every patient, I am plotting. So let's say this patient, right? For this patient, this is the weight and this is the height of the patient, right? So for this patient, each patient is represented with a cross. This is the weight of the patient and this is the height of the patient, which means my variables or features now are height and weight, right? Simple. Similarly, this is another patient for whom this is the weight and this is the height. Simple. Now I've also color coded this in such a way that patients who are diabetic are marked in orange cross. Patients who are not diabetic are marked in blue cross. Look at this. The moment, see what am I doing here? I'm doing a simple plotting. I'm taking each patient, I'm taking the two variables corresponding to the patient or two features corresponding to the patient, which are width and height, right? And what am I doing now? All that I'm doing now is simply taking, plotting each patient in this plot. It's a very, very simple plot. This is something that we have learned as high school students, right? As probably in our 7th or 8th grade. Now comes the fun part. I've also color coded each of these crosses, wherein I'm saying if you're a diabetic, it will be orange. If you're non-diabetic, it will be blue. Very simple. Now looking at this diagram, what can you conclude? Again, the whole purpose of data analysis is to analyze data, is to come with conclusions from data, is to make sense out of data. Now given this, there are a couple of very simple things. Again, this is called a 2D scatter plot. Okay, so this is what is called a scatter plot. Again, this is one of the simplest and most easy to understand plots. Why is it called a 2D plot? Because you have two dimensions, weight and height, right? Similarly, you can do 3D plots. Again, beyond 3D, we can't visualize as humans, right? I don't think any one of you can see in 4D, right? So given this, look at this, given this, what is a simple analysis or a conclusion that I can arrive at? There are a couple of very simple analysis and conclusions that I can arrive at. First thing, people who are heavier, see the weight here is more. If you look at all these people, the weight here is more. So people who are heavier tend to be more diabetic. Of course, there are a couple of diabetic patients here also whose weight is less, but more likely if a person has more weight, look at this, these people are heavier and also shorter as compared to these people. Look at these people. Look at these people. This person is the same weight as this person, but this person is also significantly taller. This person could be a 6'2". This person could be a 5-footer. A 5-footer who is also, let's say, 100 kilos. Let's assume this is 100 kilos. A 5-footer who is 100 kilos is more likely to be obese and hence a higher chance of them being diabetic. So by just looking at the simple diagram, simple scatter plot, I can come up with some important observations that people who are heavier tend to be people who are heavier and shorter, and not or, and shorter. Because if you look at these people are shorter, but they're not heavier. Maybe they're kids or maybe they are smaller sized women, right? Women tend to be typically shorter and lower weight than men, right? Kids obviously will be of smaller height and lower weight than adults. So one important conclusion here is that most diabetic patients tend to be overweight for their height. See, just from this simple plot, it's a very important conclusion that we arrived at, right? So that's one of the purposes of plotting. The purpose of plotting is to find visual patterns which we can read from this plot. Again, I often tell this in our course also, that plots is like the art of mathematics. So the whole of mathematics has two parts, broadly speaking, right? There are plots and diagrams and plots, and there are equations. Again, this is my personal feeling or my personal opinion. Diagrams and plots are like the art of mathematics. Equations are like the poetry of mathematics. Because in poetry, you try to represent great ideas in a very short sentence. So are equations. You're trying to explain brilliant mathematics, brilliant ideas in very short, crisp equations, right? So plotting or diagrams in general is one of the most important areas of mathematics overall, but also very specifically for AI. AI is just applied math if you think about it, with some programming thrown in there, right? So this is one of the simplest forms of plotting, and plotting is extremely essential because you can find visual patterns by doing 2D and 3D plots. Again, this is just one of the plots. This is called a scatter plot. There are tens of plotting methods. They're like, I at least have encountered close to 100 plotting methods in various areas of machine learning, AI, applied mathematics, computer science, etc. There are tons of ways, literally. Okay, I have personally seen almost maybe close to 100. I have never counted it, but I think I've seen at least a few tens of plotting methods. This is the simplest. Of course, in the interest of time, I can't, if I start telling you 4 or 5 other types of plotting, I'll have to go into the mathematics behind them. So I hope you've got a sense of why plotting is important and necessary for data analysis, and how data analysis itself, how we can analyze data and come with important conclusions based on simple plotting techniques. Again, I'll be using this data set or this diagram as a running example through the rest of this live session also, right? I hope this example is clear. Okay. So the next big area, again, please understand that I'm covering many of these topics in just a few minutes. Plotting itself, if you go and understand at least the top 10 types of plotting, it will take you a few hours of learning, right? I think in our course videos, we'd spend, I think, close to 3 to 4 hours just discussing a few plotting techniques, right? So again, I'm going through fast because we have a 2-hour limit where we want to get a broad overview. Next thing is the whole area of probability and statistics, right? Again, this is something that some of you may have learned during your undergraduate days, but many of you never understood why the heck are you learning it. Probably you're learning it to pass exams. You might have, again, there is a lot of terminology in here. I'll not be going into density functions, mass functions, distribution functions, all of that. I'll not be going into it, but let me give you a simple intuitive understanding of why probability is useful. Suppose if somebody can tell you the probability, okay, so if somebody can tell you the probability of a person being diabetic, given, again, this is a mathematical expression. You can read it in English. Any mathematical expression you encounter, try to read it in words. So the way to read this is, again, you might already know this. So this is called as a conditional distribution. What it means is this: what is the probability that a patient is diabetic given that a person weighs more than 120 kilograms? This probability will be very high typically. If somebody is weighing more than 120 kilograms, again, there are two options here. The person may be short or tall. If the person is tall, mostly if the person is like 6'4" or something like that, very low chance of the person being diabetic. But if the person is short, there is a higher probability. But here we are not given any information about the height. We are just given weight. The probability may be, let's say, 50% or 0.5. We write 0.5 or 50%, which means if you find a person who is, again, I'm just making these numbers up. I don't know the exact numbers. Okay. So if this probability is this, again, you can compute these probabilities very, very easily. Okay. Given some data set, these are very simple stuff to calculate. But what this gives you is, again, by just looking at the probability, you can say, if you find a person who is over 120 kilos, irrespective of their height, there is a 50% chance that they are diabetic. Right? And that's a very important analysis or conclusion. Data analysis is all about understanding data. Similarly, let's take a slightly more complicated example. What is the probability that a person is diabetic given that the person is over 6 feet, right? Okay, so let me change this. I think I did a mistake here. So the probability that the person is diabetic given the person is over 6 feet tall, and let's say the weight is, let's assume the weight is less than 100 kilos, less than equal to 100 kilos. This probability will be low because it's very common to find 6-footers, right, who are 90-95 kilos also. So this probability might be only 10%. So this says that if you're a 6-footer and if you're less than 100 kilos, your chances or your likelihood of being diabetic is quite low. Similarly, there could be other features, just like you have your height and weight features, there could be other features like gender, like age. So what is the probability that somebody is diabetic given that their gender is female and the age is over 70 years? Let's assume this probability is 0.18, which means 18%, right? Again, there could be many other features and variables. So these simple conditional probabilities, again, these are called as conditional probabilities. These conditional probabilities can give you a very good intuitive understanding about what's happening in the real world, right? So what this says is, there is an 18% chance if you are over 70 years old and female that you're diabetic. Again, I can make this more complex, and suppose if I start writing it like this. Suppose the probability that I am diabetic, given that the person is female, aged over 70 years, and let's assume weight is greater than 80 kilos, such a probability will be much higher, because females over 70 years do not tend to be 80 kilos or over. And let's assume height is less than equal to 5 feet 5 inches. Right? This probability will be very different. This probability could be as high as 60%. Right? This probability could be as high as 60%. Right? So conditional probability, again, this can be computed very easily given some data. And these conditional probabilities is a very simple concept in probability, not even in statistics, which can help you make important conclusions about data. Of course, there are many other concepts that I am not touching upon, which are your probability density function, mass function, CDF, etc. Again, just learning, forget about statistics, even basics of probability itself is a few hours of learning. I'm just trying to give you an intuitive understanding of where probability fits into data analysis and how data analysis itself fits into AI, right? So next thing, very important, since we are in the corona world or in the corona lockdown, suppose you want to design a drug or a medicine, right, for treating coronavirus. This is where statistics is very, very important. Again, there are almost 70 drugs or medicines. Again, drug is a more American word, medicine is more of a British Indian word. So there are almost 70 medicines which are being tested by various governments, organizations like WHO for coronavirus. And one of the things that, again, statistics is one important part with lots of applications in medicine, right? So what they do is this, they take 1,000 patients. Okay, again, I'm simplifying it a lot. They take roughly a good number of patients. They break them into two groups. One group is called as a control. The other group is called as treatment group. So both these groups, for example, let's assume all of these 1,000 people are, let's assume, infected, right? Infected with, let's say, coronavirus, right? All these people, of course, some of them may have milder infections, some of them may have severe infections. So what they do is they break this group of 1,000 people into two groups. For the second group or the treatment group, they will give a new drug that might work, right? So there is this drug called Remdesivir, right, which is being experimented extensively for coronavirus. I was reading some research papers on it. Of course, I don't know any biochemistry, but I was reading the analysis of their A/B tests or control treatment tests. These are also called as randomized trials in medicine. I was reading some of this data analysis, right? So let's assume there is a new drug or a medicine. The treatment is given that, right? The control is also given a medicine, but this medicine capsules look exactly like this, but there is no medicine inside that. Those are called as placebo medicines in healthcare and medicine. Because probably just by taking a medicine, people will think I will become better. So they want to account for that placebo effect, right? So they're given a medicine, but that medicine is basically an empty capsule without anything inside, right? So these people are given a drug with a chemical like Remdesivir in their Remdesivir or any other chemical drug that they're testing, right? So there is no chemical in this, there is chemical in this. Now in the control group, let's assume 65 people recovered, let's say after 7 days. Let's assume after giving this medicine for 7 days, 65 out of 500 people recovered. Okay, there is no medicine was given to them. There was just a capsule that is given with no medicine inside. But probably these people had good immune system that they could fight it off. On the other hand, of the 500 people, let's assume 475 people were cured. Probably everyone except extreme severe cases were cured. Now this is how actually drug testing happens. Now if you look at this, of course, they compute a bunch of statistics on top of it. They say that this difference of 65 versus 475 is statistically significant difference for us to push this new drug into the market, right? Or to give this new drug to patients. Let us all hope that the 70 or so drugs that are being experimented with, some of them will work out and we come out of this coronavirus pandemic as soon as possible, right? But this is one other area. I wanted to specifically pick this example. These are called as randomized trials, or these are also called as A/B tests. In our course videos, we described them as A/B tests in depth, in detail, right? So the statistics part, again, statistics has all of these. Again, there's a lot of more mathematics and statistics on top of it. What I'm giving you here, again, these 500 split is random. I forgot to mention that. Out of these 1,000 people, 500 random people are put here. 500 random people are put here. A simple way to do it is to do a coin toss. Take a fair coin with heads and tails, toss it for every person, right? Just a second. Yeah, so 1 second. I'm just looking at some suggestions that you guys have given. Actually, my team is summarizing because I'm not looking at the chat window. Okay. Test exercises at the end of walkthroughs. Okay. Okay. Some of you have given some good suggestions, not specific to this live session, but on other topics. We'll try to do that in the future live sessions. Okay. My team just shared the summary of some of the live sessions, some of the comments that you guys are putting in the chat window, right? But anyway, I don't think we can finish this if you do not stick to the course. I don't think we can finish this whole thing in 2 hours, right? So let's stick to the plan now. Probably we can do more live sessions in the near future. Let's try to do it, trying to cover some of the suggestions that you guys made. I'll surely try to accommodate those, right? But I think in this live session, is there anything? Going through code is not possible, unfortunately. Data cleaning, probably we can do a live session on that. Underlying working. Okay, sounds good. So, okay, I think most of these suggestions are not relevant to this live session, but we'll try to do more live sessions on those topics without doubt. Okay. So there is a bunch of statistics which will help you. Statistics, again, AI is a broad term. AI doesn't just mean robotics, right? Even classical statistics, which is used to design drugs, is something that is very important for a statistician to know about, right? So again, the next big area, again, please understand that I'm going through topics very, very fast because I want to spend some time on deep learning algorithms also. If time permits, if you can finish this in under 2 hours, very good. I'll surely go back and answer some of your questions and spend more time with you, right? So I'll take a break after the data analysis itself is over, and I'll look at some comments and try to answer them before I jump into classification, regression, etc. I'm just concerned on the time. Okay, so the next topic is within data analysis. The next very important mathematical tool is linear algebra. This is something that you may have learned in your mathematics courses. This is all about vectors, matrices, right? So these are concepts that you may have learned in your undergraduate days, in your first year or second year of undergraduate, right? Some of you, of course, we have learned some of this even in our 11th and 12th class. Again, this is extremely important area for whole of AI. Now, again, a vector can be imagined to be many things. A computer scientist will say a vector is different. A mathematician will say a vector is different. A physicist can have a different interpretation of vector, but I'll talk about vector in the context of AI. Suppose if you're given a patient, or if you're given a person, right? If you're given a person X, and you're given data about multiple features or variables. First variable is height. The second variable is, let's say, weight. The third variable is, let's say, age. Fourth is, let's say, gender. Fifth is the waist length. Okay, the last one could be, does he do exercise regularly? Or how many days of exercise do they do in a week? So if you imagine, there could be any number of such features or variables to represent one person. Again, all these are data that a domain expert, like a doctor, right, or a pharmacist could say, okay, these are the important parameters that we can use, or these are the important variables that we can use to determine whether a patient is diabetic or not, right? Again, who told us that these are important? It is a doctor. It is a domain expert. That's very, very important. It is a domain expert, in this case, probably a diabetics expert or anybody who knows medicine, right? It is a suggestion given by them that, okay, these are important variables that can help you determine whether somebody is diabetic or not. So what do? We take each patient, we represent them as an array of D values. Let's assume there are D such features. We represent them as an array of D values. Again, I'm using the computer science terminology here, right? An array of size D is, from a computer science standpoint, can be thought of as a vector of D dimensions. This is often called as a D-dimensional vector in AI, right? So this is one way of looking at it. There is a mathematician's way of looking at it, which is, okay, again, this is the same diagram that we saw earlier, okay? This is my weight axis, this is my weight, this is my height. Each of these crosses represents a patient. So let's take this patient, let's take this person. Let me not use this color. Okay, so let's take this patient, right? This patient, now I have two features here, right? Weight and height. So I can represent this patient or this person with a two-dimensional, with an array of size 2, right? So this is basically an array of size 2, right? I can also think of this as a two-dimensional vector where my x-axis is this is my y-axis. So given any d-dimensional vector, you can think of it as a point. What is this? This is a 2D space. This is a 2D space, right? This is one dimension, this is the other dimension. So you can think of a d-dimensional point or a d-dimensional vector as a point in a d-dimensional space. Again, this is 2D, right? Imagine 3D. How does 3D look like? There will be one axis coming out of your computer screen towards you. Suppose you have weight, height, and age. So the third one is coming towards you from the computer screen, right? Now this point now is flying, is in the air somewhere, is in this 3D space. Each point we can represent again using a three-dimensional vector. So the whole purpose of linear algebra is in the context of AI. Linear algebra is a very big field with many applications. In the context of AI and machine learning, the purpose of linear algebra is to take ideas from 2D and 3D that we can clearly visualize, understand, and study, and take them to a d-dimensional space. See, none of us can see a 4-dimensional space. Again, the physicists have the concept of 4-dimensional space, with the 4th dimension being time. Again, we are not looking at the physics interpretation. We are only looking at the computer science interpretation and the mathematics interpretation, right? So anything which is in 4D space, we simply can't even imagine or visualize, right? So the whole purpose of linear algebra is a mathematical tool that we have at our disposal to take mathematics and intuition and ideas from 2 or 3D to higher dimensional spaces, since we can't visualize higher dimensional spaces, right? That's where linear algebra fits into this whole idea of AI, right? The next concept, again, this is also a big overview. So the next concept related to linear algebra is this concept called dimensionality reduction. Imagine if somebody gives me a d-dimensional data. Let's assume d equals to some 20. Right? Let's assume each person is represented, or each patient is represented using 20 features or 20 variables. Right? Let's assume they are represented by 20-dimensional data, 20-dimensional vectors. Now, if I want to visualize this data, I simply can't visualize anything which is in d dimensions. One way to visualize this, again, dimensional reduction has many applications. One application is visualization, right? So in the visualization application, imagine if I can somehow reduce the data from d dimensions, as the name says, dimensionality reduction. I want to go from a d-dimensional space to, let's say, a 2-dimensional space or a 3-dimensional space, because I can plot data in 2D and 3D. So let's take 2D. So dimensional reduction is all about reducing the data from d dimensions to d dash dimensions while preserving as much information as possible from the d-dimensional space, right? So that's the whole objective of dimensional reduction. Again, there are multiple techniques: principal component analysis, singular value decomposition. There is t-SNE, which is a very interesting idea, and many more techniques. We cover at least these 3 techniques in lots of detail in the course videos, including the deep mathematics behind them, right? So one very interesting idea is this idea of t-SNE. t-SNE is a very advanced idea, state-of-the-art, one of the state-of-the-art algorithms, if not the state-of-the-art, for dimensionality reduction and visualizing high-dimensional spaces. So again, I've taken this diagram from this blog, very nice blog. Again, for any diagram that I borrow from other places, I try to give credits just below that. Again, I'll share this whole document with you so that you can go ahead and read other sources if you intend to, right? So what they do here is this. So they've taken, let's assume we have 20-dimensional data, and this 20-dimensional data is reduced to, let's say, 2-dimensional data, and I'm plotting this data in the 2 dimensions. Again, these 2 dimensions will not be your height and weight. We don't know what these 2 dimensions actually mean in the real world. But what t-SNE, this is t-SNE, right? What t-SNE tries to say is, if you take any 2 points here, okay, let me draw it here. If you take any 2 points here in the t-SNE plot, points which are close to each other, which are physically close to each other. So let's take this point, okay, let's draw it, okay. So let's assume I have point A, point B, which is very close to it, point C, which is very far from it, in the high dimensional, in the d-dimensional space, right? In my d-dimensional space, let's assume point A and B are very close to each other and A and B are very far from C. Now I want to now move this data to a two-dimensional space. What t-SNE does is, t-SNE basically means t-distributed, don't worry about it, stochastic neighborhood embedding. The neighborhood embedding is the important part here. The neighborhood embedding basically means the 2 points which are close to each other in the d-dimensional space, I will get this data into 2 dimensions such that A and B will also be close to each other in the 2-dimensional space. And I'll try to ensure that C is also as far as possible in the 2-dimensional space. Okay, so what t-SNE is trying to do is, t-SNE is trying to preserve neighborhoods. Since A and B are close to each other, they are in the same neighborhood, right? That's why it's called stochastic neighborhood embedding. So what I'm trying to do here is, given a large high dimensional data, I'm trying to reduce it into a lower dimensional data or 2-dimensional data. Again, the moment it's in 2 dimensions, I can plot it like this and visualize it. Now these 2 points are close to each other. Because they are close to each other in the high dimensional space, I'm trying to ensure that I get a 2-dimensional representation where they're closer to each other in the 2D space also. This is the whole purpose of dimensional reduction. Again, this is one of the applications of dimensional reduction. There are many other applications. t-SNE, PCA, there are tons of algorithms here, right? So with this, we have covered some of the key ideas. Again, oh, it's already 10:40. Okay, I think, okay, I'll take a couple of questions and then, because I have many more topics to cover, it's already 10:40. I might stretch this by 15 minutes if we fall short of time, right? But I hope you got a sense of, again, the idea in this live session is to get a big overview. Plotting is important because you want to find visual patterns in data. There are tons of types of plotting. Probability to make interesting and important observations and statements like this. Statistics, again, statistics is a broad field. One of the applications in the current context is in the design of drugs and testing of drugs in the real world. Linear algebra helps us understand and build mathematics to work in high dimensional spaces. Get intuition from low dimension space, but build mathematics in high dimensional space. Dimensionality reduction, one of the applications of it is to visualize high dimensional data because we can't visualize it anyway otherwise, right? So let me go to the live window itself. Is t-SNE related to Hilbert spaces? No. Hilbert spaces is a concept that you get in support vector machines. t-SNE doesn't use the concept of kernelization or kernel spaces. t-SNE doesn't. Okay, so any other questions? So do we have the restriction of using dimensional reduction techniques only for clustering? No, not at all, not at all. They're used for many, many things, clustering being one of them. I'll talk about clustering also in a little while. Explain some more examples of t-SNE. I'll provide you reference links with this document. You can go through that. Again, look at this, the time is already 10:42. We'll have to stop it at 12 to 12:15, right? So again, don't confuse yourself. SVM is a classification technique. t-SNE is a dimensionality reduction and visualization technique. They are two different things, right? So somebody is asking, this is a very good question, Asresh. So if you read the main topics, can we be eligible for data analytics jobs? Again, data analytics jobs, again, I'll answer this question and I'll go back to the live session itself. So for data analytics jobs, you need to be good with programming, preferably Python or R, any of the major programming languages for sure, number one. Number two is you need to be good with probability statistics, linear algebra, and plotting, without doubt. That's super critical for data analytics jobs. Number two. Number three, you need to be good with SQL, right? Because SQL is extremely important for acquiring data and doing some simple data analysis, right? Number four, you may not be an expert in a lot of machine learning and deep learning techniques, but you need to know at least a few basic ones. You need to know things like k-means, things like logistic regression, things like basic techniques. I'm not asking anything fancy. Basic techniques like PCA. So typically for data analytics jobs, programming is important, number one. SQL is important, number two. Number three, probability, statistics, linear algebra, dimensionality reduction is important. Number four, a few techniques, maybe three or four, maybe one technique from classification, one technique from regression, the most popular logistic regression type, very simple techniques. I think that's good enough for most data analytics jobs, right? So, okay folks, so back to our discussion. So, next thing is classification. Now, what does classification basically mean? The name itself says this, right? Classification basically means, okay, the task is very simple. Given a patient X, let's assume I'm given two features, right? For each patient, let's assume I'm given height and weight. So, given these two data, given just this data, I have to classify this person. I have to classify this person as either diabetic or non-diabetic. Right, so this is basically this is called a two-class classification, because given any new person, again, the way it works is our whole objective is given any person, right? Given any new person, given just their height and weight, can I determine if they are diabetic or non-diabetic? Or in other words, what logistic regression? Again, let me give you the intuition behind logistic regression, right? So what logistic regression does is very simple. Okay, again, let's take this data. Okay, very simple. I'm using the same example. X-axis is weight, y-axis is height, and this is the data that I have. Again, this is called as a training data. I'm given some data using which I can build a model. Logistic regression is one of the modeling techniques. It's one of the simplest but a very powerful technique. So in logistic regression, what I want to do is this. I want to find a line. Look at this. I want to, let me draw it carefully. Suppose I want to find, okay, I have to be careful. Okay. So in logistic regression, my objective is to find a line, right? In 2D, this is a line. This is a 2D space that, again, I'll give you examples from 2D. In a 2D space, this is what is called as a line. In 3D, instead of a line, we will find a plane, right? In 2D, we will find a line. In 3D, instead of finding a line, we'll find a plane. We all know what a plane is, right? In 4D, we will find something called as a hyperplane. The concept is the same, and the whole mathematics of line, plane, hyperplane, everything comes from linear algebra. That's why linear algebra is so important, right? So again, what is our objective here? Our objective is, given this data to us, given these orange points and blue points, I want to find a line that separates the blue points from the orange points. Of course, I can't do it perfectly, because look at this. If I draw this line and say all the points to the left of this line, to this side of the line, are all non-diabetic, everyone to this side are diabetic. That's not fully true, because there is a blue point here and there are a couple of orange points here. But most of the points which are there on the left side are non-diabetic, right? Most of the points which are on the right side are diabetic, right? So this line is what the logistic regression model tries to find, right? Now, once I have this line, very interestingly, now I can do a lot of, so I'm given a bunch of data. Using that data, I have built this model now. Now, using this model, what can I do? Suppose if a new patient comes, this is the power of machine learning, right? Suppose a new patient comes, okay? The new patient, let's assume the new patient has, again, a height and a weight. I plot him on this 2D space. Let's assume the new patient falls here. The likelihood that this person is positive is very high, if you think about it, right? Because he is on the right side. He is on the right side of this line. If the new person is here, then very likely this person is non-diabetic, right? So again, if a point is, let's say here, if a point is here, let's look at this. If a point is here, very close to this line, then there is a probability that this person is non-diabetic, but the line could have tilted slightly this side or that side, and this person could have been classified as diabetic or non-diabetic, right? You got that, right? So points which are closer to the line, you will say the probability of the person being diabetic, given the person's information, given X. X is nothing but the features or the variables corresponding to the person, right? If this X is closer to this line, the chances that they are diabetic or non-diabetic, you have to be less certain. But if they're farther away, suppose if I have one of the new patients here, oh, this patient looks very similar to this guy, and this person is very far away from this line. So very likely that this person is a diabetic, right? So logistic regression tries to give us, given any new point. So first, given the training data, given some data like this, it will train a model. What does training a model mean? Training a model is nothing but finding this line. Now, once it finds this line, given any new patient, it can tell you the probability that the person is diabetic given the features corresponding to this patient X, Number one. Number two, right? That's what logistic regression does. It is trying to find a line, plane or hyperplane depending on what space we are operating in. Its overall objective is to find a line that separates diabetic patients from non-diabetic patients. And the big question here is, how does it determine this line? How does it detect this line? It does it using a mathematical area called as numerical optimization, right? Again, you might say, oh, this sounds too complex, but numerical optimization is a very simple technique. We all learnt in our 11th and 12th class, right? Finding minima and maxima. If you recall, we learnt about finding minima and maxima in calculus. If you remember, if the derivative of any function with respect to x is 0, this function at this point we can have minima or maxima, if you recall. If you remember this, I've written partial derivative, but okay, because we typically use partial derivatives in AI and machine learning and not regular derivatives, right? But imagine if you have this, that if the derivative of a function with respect to x is 0, at that value, at let's say some value x0, then that point is minima or maxima. This is your 11th class, this is not even 12th class differential equations. This is, I think, the first thing that you learn in your calculus in your 11th class. Numerical optimization is a simple extension to maxima, minima that you learn in your 11th class mathematics. If you just recall, again, some of you may have forgotten your 11th class mathematics, but if you refresh your 11th class mathematics, understanding numerical optimization is very simple. Numerical optimization is the mathematical area which is built on top of calculus, minima and maxima, and this is used to find this line by solving something called as an optimization problem. Again, I'm not going into the mathematics behind it right now in the interest of time, right? So I hope this is clear. This is what logistic regression does. Next comes SVM, right? So SVM, okay, so now look at this. Again, I've changed the data set slightly. If you notice, I changed it because it will be easier for me to explain with slightly different data set. Now here I have multiple options. I can draw my line. Again, within SVM there are two types of SVMs. There is linear SVM and there is kernel SVM. First, let's talk about linear SVM. In the linear SVM, what we are trying to find here is, see, if these are all my points, right? I have two options. I have multiple options actually. I can draw my hyperplane like this. I can also draw another hyperplane like this. I can draw a hyperplane like this. I could have drawn a hyperplane like this. I could have drawn a hyperplane like this. There are so many hyperplanes or so many lines. Again, I use the word hyperplane because I'm used to that. There are so many lines that I can draw to separate the non-diabetic patients from the diabetic patients. Out of all these lines, which line is the best line? That's a good question to ask, right? There are so many lines that are possible, right? So what SVM says is, what linear SVM says is, let us try to find that line. Okay, let us try to find that line. Okay, I have to be careful when I draw this. Okay, so it will say, okay, I'm just drawing it. Okay, so it will say I'm trying to find that line wherein if I draw this line and if I draw a parallel line to this which passes through the first non-diabetic patient, right? The first point. Again, all these three hyperplanes are parallel to each other. All these lines are parallel to each other, right? Again, this is my, I call this my hyperplane or line. Okay, let's call it line 1. Let's call this as line 2, line 3. Okay, all these lines are parallel to each other. Now, how did I draw these lines? I drew this separating line or separating hyperplane, and I drew L1 and L3 to be parallel to that L2 passes through the first point here. See, as I keep moving this side, I find the first non-diabetic patient and draw a line through that. As I keep moving towards this, I find the first diabetic patient and draw a line through that. This gap that I have is what is called as margin. So what SVMs teach us, again, through a bunch of very beautiful and advanced mathematics, what they explain us is the best hyperplane is a hyperplane that maximizes the margin. So SVM is also called as a margin maximizing hyperplane or margin maximizing classifier, because there are so many lines that I can draw. For each of such lines, I'll compute this margin. This is what is called as margin, right? And I'll try to pick that line which maximizes the margin. Again, this is also found out by solving numerical optimization. See, most of AI and machine learning algorithms are solved using numerical optimization algorithms, which are based on calculus themselves, right? So, okay, sounds good. So, again, this is the crux of a linear SVM. Again, if this was all SVM did, SVM wouldn't have been so popular. There is something called as kernel SVM. Okay, this is the true power of an SVM. Again, I've changed the data here. Look at this. Okay, I wanted to explain this. Imagine if this is my data. Can you draw any line? Look at this data. In the real world, data never behaves that well. Okay, data is crazy like hell. Can you draw any line that separates the blue points from the orange points well enough? Suppose if I draw a line like this. Again, there is a bunch of orange points here. There is a bunch of blue points here. So this line won't work, right? Suppose if I draw a line like this won't work because I have a bunch of orange points here. By just drawing one line, I can't separate my diabetic patients from non-diabetic patients. I can't do it. So the idea of a kernel SVM is, kernel SVM says, given this data, I'll apply a beautiful concept in mathematics called as kernelization and Hilbert spaces. Of course, I can't go into the depths of it now, wherein I take this data, I project this data to a high dimensional space. So here my data is two-dimensional with weight as one axis, height as other axis. I'll project this to a completely different space with completely different features. Sometimes I don't even know what these features are, right? Such that all of my diabetic patients are grouped together. All of my non-diabetic patients are also well grouped together. Now, if they're well grouped together, and if I can find a margin maximizing hyperplane. So kernel SVM says, in the real world, data is not linearly separable. What does linearly separable mean? I can draw a line and separate the data, separate the two classes, or separate diabetic patients from non-diabetic patients. So that's not possible every time. In some cases it is possible, but in many cases it's not possible. So what kernelization tells you is, let me take this data from this space to another space using a trick called as a kernel trick, such that in this space, probably, this data, I can find a hyperplane in this space, in this 3D space. This is not a line, this is a plane now. Okay, I can find a 3D plane. Here we are going from 2D to 3D. In the real world, you can go from 2D to any other high dimensional space. So I'll find a plane here such that everything to the left of the plane is mostly diabetic patients. Everything to the right of the plane is mostly non-diabetic patients. Again, all this is done using numerical optimization and some fairly ingenious mathematics called as the kernel trick, right? Again, somebody was asking me earlier, right? Kernel trick takes the data from low dimensions to high dimensions. T-SNE takes the data from high dimensions to low dimensions. They're two different things. Okay, so that's what your SVMs are all about. Next comes your decision trees. These are very, very powerful ideas. So imagine, again, I'm taking this data. Okay, so again, I'm taking this data. Okay, I can't find a single line to separate this. But the idea behind decision trees is, why should I find a single line? Why can't I find multiple lines like this, both vertical lines and horizontal lines? Again, remember, note that these lines are not oblique. They are called as axis parallel lines. These two lines are vertical lines which are parallel to this axis. These three lines are horizontal lines that are parallel to the x-axis. So decision trees at the core, what they say is, why should I find one line? Can I find axis parallel lines or planes or hyperplanes? Why can't I find multiple lines like this such that suppose imagine through some mechanism. Again, decision trees uses some very ingenious algorithms. Decision trees tries to find these lines not by solving a numerical optimization solution, but by coming up with a very ingenious computer science algorithm. See, AI is in the intersection of so many areas. Okay, it uses a very ingenious computer science algorithms to find these vertical and horizontal lines such that this whole region is now all non-diabetic patients. This region is all diabetic patients. This region is all non-diabetic, diabetic, mostly diabetic, diabetic, non-diabetic. Now, how do you represent this? because this was designed by computer science folks. Decision trees is a concept from computer science and data mining and databases community, right? They said, okay, this is the one way to visualize the decision tree. But since this is designed by computer scientists, they said we can write it as if-else conditions. Look at this. Let's look at this, right? So if I write a condition like this, if my weight, suppose if weight is less than equal to W2, let's assume this is W2. Okay, this is W2. If weight is less than W2, which means all the points which are in this region, all these points which are in this region, right? If weight is less than, look at this, if weight is less than equal to weight 2, which means this region, and if height is less than h1, okay, if height is less than h1, what does that mean? Everything which is below this line, everything which is below this line. So what is these two conditions telling me? These two conditions are telling me this whole region. It is telling me this whole region, right? What they're telling me about is this whole region. So simple if-else conditions can be used to determine these axis parallel lines or planes. Look at this. If my weight is less than W2, sorry, there is a small error here. Sorry, my bad. So weight has to be, sorry, let me erase this. Sorry. Weight has to be less than W2, right? Which means only till here. And height is less than H1, which means this region. So intersection of those two, because it is if, nested if within if, right? So that will be this region. That will be this region. This region. Now, if you notice in this region, you only find diabetic patients, right? So what do? Decision trees using simple algorithms tries to come up with these if-else conditions, which can be visualized as this axis parallel lines, wherein you say, if the weight is less than W2 and if height is less than H1, those patients are all diabetic, or yes, diabetic, right? Look at this. You can represent a decision tree as a simple nested if-else conditions. I mean, while other techniques like SVM and all are super powerful, they're beautiful mathematically. What I really love about decision trees is their simplicity. Like everyone who learned basics of programming knows about nested if-else conditions. Axis parallel lines is something that kids understand, right? So instead of looking at all the beautiful mathematics of kernelization, SVMs, logistic regression, decision trees are very, very powerful and they're very easy to understand. If somebody gives me this rule book, I can say when to determine somebody is diabetic or not. I can just read these rules. These are simply like rules that we can easily interpret and understand. That's the beauty of decision trees, right? So with decision trees comes the next technique called as ensembles. Okay. There are two types of ensembles. The first one is called random forests. The other is called GBDTs. Again, you can build an ensemble basically means a group of models. Instead of building one model, can I build multiple models? It's like having experts in multiple fields. Imagine instead of taking a decision from one person, take decision from multiple experts and finalize the decision based on the feedback from multiple experts. That's what an ensemble basically means, a group of models, right? Of course, there are fundamental mathematical differences between how random forest works and how GBDT works. But the core idea is this. And again, in practice, ensembles are built using decision trees a lot. You can build ensembles using any model, but in practice, decision trees are used extensively for ensembles. Again, in classical non-deep learning machine learning, random forest and GBDT are the most widely used models pre-deep learning. In many instances, random forest and GBDTs can perform better, more efficiently than even SVMs in practice. So that's why there was a time pre-deep learning when every major company you can think of, every major company, Google, Facebook, Amazon, Netflix, you name it, all of them were effectively using some random forest or GBDT algorithm for tons of models that they were designing. Okay, I have built tons of these models myself at Amazon. Okay, this is pre-deep learning. Deep learning came and changed many of those things, right? So, but it's important to have a context. Okay, what does random forest do? Random forest says, imagine if this is my total data that is given, this box is the total data that is given to me. So what it says here is, let us take a random part of the data and build my first decision tree model M1 on this data. Let's take another random part of the data. Of course, this data could be overlapping also, right? Some data could be overlapping also. Take another random part of data and build the second decision tree based on that. Take another random part of data, build third model. Build many such models. Now what happens is, suppose if you give a new patient, model 1 might say, yes, this person is diabetic. Model 2 might say not diabetic. Model 3 might say diabetic. So what you do here is you do something called as majority voting. What it means is, you say what majority of these models are saying. In this case, let's assume we have only 3 models. Typically we train tens, even hundreds of models. Okay. So in practice, so out of these 3, 2 people are saying that the person is diabetic. So majorities are saying diabetic. So this person must be diabetic. Again, I'm simplifying the intuition. Basically what you do here is you take a random part of your data, train one decision tree model, take another random part, train one more model, and so on and so forth, and do a majority voting on all of it. This is one form of ensembling. The second form of ensembling is called gradient boosted decision trees. Extremely powerful concept. Wherein on your total data, now what you do here is this, on your total data you build model 1. Your model 1 will have some errors. No model is perfect. Now what is an error here? Let me show you. Suppose if I build this model, okay, this is an error point because this will be misclassified. While this person is actually diabetic, we are going to call him non-diabetic based on this decision tree model. Similarly, this is an error, right? So what we do now is in GBDT, we first take the whole data set. Of course, we can do some randomization here also, but in general, you build a model, you get some errors. Now you build your second model such that you correct for these errors by giving more importance not to make mistakes on these errors. Now after doing model 2, so first you apply model 1, it will generate some errors. Then you train your model 2 such that you avoid these errors. Then this will again create some errors, right? Now once you create these errors, you will again build model 3 to correct for the errors that model 2 has made, and so on and so forth. So think of this as a sequential system wherein you build one model, it will have errors. You train the second model such that these models can be reduced or completely mitigated, but then this will create more errors, so on and so forth, right? That's how you create multiple models and combine all these models. Again, this is a very high level overview of the topic. Okay, sounds good. Now let's go into regression. We'll quickly go over regression and then jump into deep learning itself, right? I hope we can finish by 12:15, but let's see. Okay, so for regression, in classification, what did we do? We said given data about a patient, we said whether the patient was diabetic or non-diabetic. That's what we said. Here we don't want to do that. We want to estimate a numerical value. For example, given all the data about a patient, let's assume I've given the data about their height, weight, waist, age, blah, 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 blah. With all this, if I want to estimate blood glucose level, again, this is some blood glucose level data that I taken from a pharma company, right? So blood glucose is typically measured in mg per deciliter, right? So this is the normal blood sugar level that you can have. This is borderline diabetic. This is high diabetic. This is very high risk diabetic. This is low sugar people, right? So can you predict this blood glucose value? Again, blood glucose value is a numerical value. So what do you want to do? Given X, so let me use this itself. Given all these variables or features about X, you want to predict the blood glucose level. Can you do that? Because what you want to predict is a numerical value. Again, most of the techniques in classification can be used for regression also. Okay, let me give you a simple example. Okay, so there is something called as linear regression. What linear regression tries to do is this. It says, at the end of the day, you want to come up with this. Blood glucose equals to some function, okay, of all the function, some function of X. Again, X itself is a vector here, remember. X itself is a vector of many variables or features, right? So you want to come up with this function. Linear regression says, let us assume that this function is a simple linear function. What is a linear function? So a linear function basically says that my blood glucose level, let's assume, is some some constant times some weight 1. These are called as weights. Weight 1, weight 2, weight 3, weight 4. These are constants that we determine while training the model, right? So it says, so what it says is your blood glucose level is basically a weight multiplied by the height plus another number, let's call that number as weight 2 multiplied by the weight of the person, another number multiplied by age of the person, another number multiplied by the gender. Again, gender you can represent 0 equals to male, 1 equals to female, because you want to represent it as numbers. So on and so forth, another number multiplied by the days of exercise. So this is what is called as a linear model. Because what are you doing? You are multiplying each of your features or each of your variables with a number and then just summing them up with plus some constant. So the whole objective of linear regression is, can you find the W1? Okay, let me change the color here. Can you find W1, W2, W3, W4, WD plus constant? Can you find all of them such that given any new patient X now, with their height, weight, age, gender, blah, 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 I can just perform this simple function F. I can simply perform this function and obtain their blood glucose level. Again, now if you notice, I can write it succinctly. Okay, I can write this whole expression in short as blood glucose is summation over I equals to 1 to D, Wi. Instead of calling each of them height, weight, etc., let's call this as feature 1. Let's call this as feature 2. Let's call this as feature 3. So on and so forth. Let's call this as feature D. Okay. So weight multiplied by the feature I plus some constant. And all we have to find here is the weights and the constant. That's what we have to find in linear regression. Now, other very important aspect here is there is something called as the parameter of the model, which is often represented using theta here. Again, I'm not going too deep into the mathematics. Here, theta is basically, see, what represents this function? What are the constants or the parameters of this function? The theta here is nothing but weight 1, weight 2, so on and so forth, weight D, comma constant. Because if you know weight 1, weight 2, weight 3, weight 4, weight D and constant, if you know these values, you can simply apply this function on any input X. That's why theta is called as the parameters of this function. Right? So in linear regression, our objective is to find the parameters of a linear function like this, right? This is part of my parameters and this is also part of my parameters. So this and this constitute my parameters. I want to find it in such a way that this expression is as close to correctness as possible. Again, this is also solved using numerical optimization, right? All this is solved using numerical optimization. This is the crux of linear regression. Very simple concept here, right? Now, so again, you can do regression using linear regression. Of course, you can do regression using decision trees, and if you can do it using decision trees, you can use multiple decision trees and build a random forest or a GBDT. Again, random forest and GBDT based regressions are very, very popular in the real world. So let's look at decision tree, because once you understand decision tree, random forest and GBDT are a simple extension to that concept. Now what we'll do is this. Again, in decision tree, what do? We just draw axis parallel lines. Here I've drawn many more lines than previously. Look at this. Here my objective is not to say whether somebody is diabetic or not. I want to actually come up with the blood glucose level itself. So I'll keep drawing these axis parallel lines smartly using an algorithm such that, so look at this, I've drawn these two. So what I want is all the people who are in this area, let's assume have the same blood glucose level. So let's assume all of them have blood glucose level 120, right? Or very close to 120. So what am I doing here? I'm basically breaking this whole space using axis parallel vertical and horizontal lines such that everybody in this chunk, let's assume, has a value which is very close to 150. Let's assume all the people in this region has a value which is very close to 140, and so on and so forth. So what I do now is I just say, okay, again, what am I doing here? I'm breaking this whole region using axis parallel lines such that in each of these boxes or regions, I have more or less the same value. So in this, let's assume the value that I have here is 130. Let's assume in this, the value that I have here is 105. So on and so forth, right? So I can again represent this using if-else conditions just like the way we have seen earlier, right? For each of, so this region, how do I represent this region? This region will be, if weight is less than W1, and if height is less than height 1, what I get is this region. So in this region, I know that typically most people have a blood glucose level of 140. So I can write it as an if-else condition and say, if weight is less than W1, if height is less than H1, then the blood glucose level is 140. See, I've just converted the decision tree concept from classification to simple regression. Now, the concepts of random forests that we have learned and GBDT that we have learned can easily be extended based on decision tree concept, right? So again, this is decision tree based regression. Next comes clustering, right? So after this, I'll take a couple of minutes break because I've been almost continuously speaking for the last hour, almost 1.5 hours now. So, okay, what does clustering mean? Clustering basically means, okay, look at this data. There are no colors here. There are no colors here. So I'm just given data about a bunch of users, but I'm not told who is diabetic and who is non-diabetic. That information is not given to me. That's why I have colored all these points in the same color, right? All that I'm given here is I'm given some data about a bunch of users. Now what it asks me, the purpose of clustering is to cluster, basically in English means grouping. It means group similar objects. Now how do you define similarity? There are many ways to define similarity in mathematics. One simple way to define similarity is proximity. These 2 points are close to each other, which means they must be similar. So the purpose of clustering is to group similar objects based, so each object here is represented again using a vector. The objective is to group similar objects, right? So here I can say, okay, this whole thing is one big cluster. That's the purpose of clustering. Now, when I group similar objects, you might say, why is that useful? Now, instead of looking at all of these users, I can look at one user here. I can take one user here, study this user, and most of the properties or conclusions that I come up with for this user also should be meaningful for all these users. Like for example, imagine I can't test everyone. Let's just assume. Suppose I have 1,000 patients, I can't test everyone. And I've clustered the data. I have this data. I have this height, weight, etc. Let's assume that the cost of doing a diabetic blood test is high. Let's just assume. So what do I do now? I clustered all these patients. I take one patient from this cluster. Let's call this cluster 1. I take this patient, I do a blood test. And I recognize that this patient is, let's say, diabetic. Now, since all these patients are very similar to this patient, it's very likely that most of them, if not all of them, most of them also will be diabetic, right? So, I mean, that's saving tons of blood tests for me, right? So, something like this can be used for data analysis. Again, clustering has its own purpose of understanding data, right? Now, within clustering, there are broadly 2 schemes. The first scheme is called k-means cluster. Now, here, k-means clustering, basically what it does is, again, I'm not going too deep into the algorithm of k-means. You first say, I want 4 clusters. You say, I want 4 clusters. Now, it will take the whole data and it will group it in such a way that I'm forming 4 clusters here. This whole thing is one cluster. This whole thing is another cluster. This whole thing is a third cluster. This is the 4th cluster. Remember, there are actually 2 subclusters within this cluster. But since I gave k equals to 4, it is only generating 4 groupings. Again, clustering algorithms, most clustering algorithms are designed using computer science algorithms. Of course, there are some clustering algorithms that also use mathematics like non-negative matrix factorization based clustering, etc. But in general, most like k-means clustering algorithm was designed by computer science folks and by databases, data mining folks, mostly computer science guys, right? So now if instead of k equals to 4, if I give k equals to 5, what happens? This cluster may be intact. This will become one cluster. This will become another cluster. Now I have 5 clusters. 1, 2, 3, 4, 5. So k-means basically is trying to find tightly packed points or tightly grouped points based on the number of clusters that I'm giving. How it does that? It's actually fairly simple, but it'll take us almost half an hour to just go through it. So I'm skipping it for now, right? But it's a very simple, very powerful, widely used clustering algorithm. Then there is a whole area called hierarchical clustering with multiple clustering algorithms within this. The whole hierarchical clustering is as follows. Imagine this whole thing is my data. Okay. Suppose imagine this whole thing is my data. Hierarchical clustering says, again, there are multiple types of hierarchical clustering. I'm giving you one example. Take this whole data. Let's break this up into 2 parts. First, it will try to break this as one cluster, second cluster. Okay, so this is basically called as a top-down approach. Take the whole thing as one cluster, break this into two clusters. Now try to break this into two clusters now further. So this could become one cluster, this could become one cluster. Break these into smaller clusters. So this could become one cluster, this could become one cluster. And again, keep doing it. Again, break this into one cluster, break this into one cluster, break this into one cluster, break this into one cluster. You can keep doing it, right? So the final diagram looks like this. This whole data broken down into two clusters. This is now further broken down into two clusters. This is broken down into two clusters, and so on and so forth, right? Very similar to the diagram that I showed here, right? So in hierarchical clustering, I don't have to say how many clusters I want. I can decide, like I can pick this whole thing as one cluster, but I can pick finer clusters here. So it gives me more control on the number of clusters and how tightly they are packed, right? So that's a whole area of hierarchical clustering. Next, this is where I wanted to spend the next few minutes. Sorry. So let me go up. So I'll take a quick 2-minute water break and I'll be back. Just give me 2 minutes, please. And we'll continue with deep learning and neural nets. I hope we can finish in the next 1 hour. So I'll try to finish in the next 50 minutes, but let's see. Okay, folks, so let's get started with neural nets. Okay, again, this is a very broad overview of neural networks. So deep learning is basically nothing but neural networks that have been there from 1950s, taken to an extreme scale, right? I'll tell you why the name deep learning. Neural networks were one of the earliest AI and machine learning models that started from the 1950s, right? 1980s was the golden age of neural networks. And the whole idea is as follows. So neuroscientists started dissecting human brain, animal brains, and they started studying the brains. So one simple mathematical model of the brain, again, this is an extremely simplified model. The actual mathematics of a neuron in the brain is very, very complex. I've studied some computational neuroscience, so I've studied even in college, so I know it's very, very complex, right? So a good simplification of it, again, throughout this 35-year period, people try to mimic the brains of animals and humans from whatever we learned from neuroscience in computer algorithms, using mathematical models, obviously. The simplest model of a neuron, again, I'm representing this as a neuron. A simplest model of a neuron is as follows, right? So there is some input is sent, some input is sent, some input is sent, some input is sent. There are connections. Again, this input could be coming from another neuron also. This could be coming from another neuron also. Some input electrical signal is sent, and based on the wiring strength, again, if the wiring is strong here, the connection between this neuron and this neuron is strong. Again, I'm simplifying it a lot, please bear with me. If the strength is more of that signal from here passes on to this neuron. So how do you represent it mathematically? You give a weight associated with this neuron. Sorry, with this connection. More the weight, more of this information should be passed. More of the data from here, or more of the information from this neuron should be passed to this neuron. So mathematically, people said, let's represent this the strength of these connections using numerical weights, number one. So what does a neuron do? Neuron gets multiple inputs. Based on the inputs, neuron computes a function. And the function output is sent to other neurons that it is connected to. This is the simplest, this is the most simple way of looking at a neuron, right? So if you look at it again, it's good to understand the mathematics behind it, right? Because mathematics is very well understood. Neuroscience, not so much. So what computer scientists, neuroscientists, mathematicians, computational neuroscientists tried to do was they said, let's build a very, very simple model of this function. So they used a bunch of very simple functions here. They said this function, again, how do you parameterize this function? What are the values that determine this function value? This function value is determined based on these weights. I get some input. Let's assume I get some input here. So let's assume there is a vector. Okay, suppose there is a vector of size 4. This first value goes in here. The second value goes in here. The third value goes in here. The fourth value goes in here. This value is multiplied by W1. This value is multiplied by W2. This value is multiplied by W3. This value is multiplied by W4. All of them are summed, and that sum goes into this function. This function applies some mathematical function, generates an output which is sent to other neurons. Again, this output will go into another neuron as input. There will be a weight associated with this again, so on and so forth. This is the simplest computational neuroscience model of a neuron. So computer scientists and mathematicians said, okay, can we take this very simple model? Again, remember, how am I representing a neuron here? I'm representing a neuron using a function with some parameters. Look at this. What is my parameters theta 1? The parameters theta 1 are the parameters of my function 1. Okay, which is my theta 1 is nothing but W1, W2, W3, W4. And given some input x, x is a vector here, right? Given some input x, right? They compute something and I get the output. Let's just call this output as y1. So this y1 is now sent to each of the other connections. So people said, now given this simple mathematical model, of course you can use many functions here. Many functions can be used, and people tried tons of functions, from very simple linear functions to highly non-linear functions. Again, I'll tell you what is a linear, what is a non-linear function in a little while. But the first work was done in 1950s. It's a landmark work on trying to do simple stuff by mimicking the computational model of a neuron. In 1980s, okay, this is people like Geoff Hinton and others. Again, Geoff Hinton is literally called the godfather of neural networks and deep learning. And because he's been working in this field for almost 50 years now, phenomenal mathematician and computer scientist. He works at University of Toronto as a professor for 6 months and at Google Research for 6 months. Phenomenal guy, right? Literally some of the big breakthroughs. He won the Turing Prize along with Jan LeCun and others this year, right? So phenomenal contributions to computer science and deep neural networks. So in the 1980s, he came up with this algorithm along with his PhD students where they said, how do we now find these weights? If I find these weights, my model is ready, right? So they came up with a very interesting algorithm called the backpropagation algorithm, right? Of course, I'll not be able to go into the details of it, but first let's understand what is a linear function and what is a nonlinear function. So a linear function basically means if this is my x, suppose my function is f of x equals to y, right? So if x is my input, a linear function basically means if I plot this, I'll get a line. That's why it's called a linear function. The line could be anywhere. The line could be passing through origin. It could be any line. But this is a line. Because this is a line, if you take the derivative of this, remember, if you take the derivative of it, it will be constant. Because it's not, the rate of change of this is constant. Right? Or in other words, a line is a linear function. Anything that is not a straight line creates a non-linear function. Right? So look at this function now. Here also y equals to f of x. This is not a straight line. This is a curved line. So that's what this is called as a non-linear function. Right? I'll show you one more very popular non-linear function. Look at this. Look at this. Look at this. Look at this. This is straight line. This is straight line. But this whole thing is my function. My function is, so let me call this as my function f1. Let's assume my function f1 of x looks like this. Looks like this. Okay. So in this region, this is all 0. From here, it's a line. From here, it's a line. Is this now? Again, this is a straight line. Remember that this is a straight line. Now, is f1 linear? No, it is not linear. Because there is, again, you can't represent this using a single straight line. Multiple straight lines is a nonlinear function. Right? So people have studied for mimicking neural networks, people have studied both linear functions and nonlinear functions. And because of a very ingenious property of functions, non-linear functions tend to work much better in practice, right? So the function that I showed you just a while ago, the function that I just showed you a while ago is one of the most popular functions called the rectified linear unit, or called the ReLU function. One of the most powerful nonlinear functions used extensively in whole of deep learning today, right? Again, there is a reason why nonlinear functions work. There is a simple mathematical proof, but I cannot go into that, right? But I hope you got the sense of it. So people said, okay, you have nonlinear functions. Now, if I have nonlinear functions, can I just stack up functions? Again, all of you may have learnt about, suppose if you have two functions, f and g, right? You can compute this, right? F of x, given x, you can compute f of x. And on the output of f of x, you can compute g of x. This is something that we learned in our school days as g of f of x. This is called function composition, right? So the same, again, this is high school mathematics. This is not some rocket science. This is simple high school mathematics, right? So what computer scientists learned was, instead of having just one neuron, if I think of this as one function, let's call it function 1, function 2, function 3, let's call this as function 4. Each function has its weights. Look at this. Each function has its parameters. The parameters for this function will be W1, W2, W1, W4, etc. So if this is my input, d-dimensional vector, again, this is what is called as a multi-layered perceptron. Let me explain that. If this is my input, I'll connect each of these inputs to a bunch of neurons. Look at this. I have 3 neurons here. I'll connect this input to this neuron. I'll connect it to this neuron. I'll also connect it to this neuron. Simply take any other input here, any other of these d values. I'll connect everything to every neuron. And every neuron has these weights associated with it, right? Every neuron has the weights associated with it. We don't know what the initial weights are. That is what we learn using calculus and numerical optimization, right? Now look at this. So what am I applying here? Given my input, let's say my input is x here. What am I applying here? I'm applying f1 of x using, f1 has, let's assume, some parameters theta1. So what am I applying here? I'm applying f1 of x using theta1, which are the parameters of this model. Parameters are nothing but, again, I explained you what parameters are, right? Just a while ago. What are the parameters of this function? All these weights, all these connection weights, right? So now what do? So I have x as input. I'm computing f1 of x1. This is f1. Similarly, I'm also computing f2. I'm also computing f3. Now these 3 outputs are now input into another function called f4. And there are weights associated with it. Let's say weight 10, weight 11, weight 12. So weight 10, weight 11, weight 12 will be part of theta 4. f4 is this function. So what am I computing here? This is nothing but it is a function on outputs of other functions, which is nothing but this, right? Look at this. Look at what I'm doing here. I'm passing x through a function. I'm getting an output, which I'm passing through another function. This is what is called a composition of functions. Here, I'm passing x through a function. That output, I'm passing it as input to another function. Same thing I'm doing here. Now, this is extremely powerful concept. The reason being, imagine if somebody just gave you very simple functions like sine, addition, multiplication, cos. This could be my f1. Let's just assume f2, f3 and f4, right? Now using these 3, again, you can think of plus also as a function. It's an operator or a function. You can think of it any way you want, right? Now given these 4 functions, I can compute very, very complex functions like this. Sine of cos x multiplied by sine x, right? Plus cos x multiplied by 1 by sine x. Look at by just using function composition. These are my 4 functions. I can combine these functions to compute a new function like this using function composition. So I can compute extremely complex functions using extremely simple functions via function composition. Right? That's the idea of whole of deep learning. Deep learning is computing a complex function output by composing or by combining multiple simpler functions. Each of these f1, f2, f3, f4 are fairly simple. They are like ReLU that I just explained a while ago. Right? But by combining them, I can compute an extremely powerful function, very, very powerful function. Actually, there is a theorem called as universal approximation theorem. Of course, proof is beyond the scope, but universal approximation theorem says any function that you have, you can approximate this function using a deep neural network, or using a neural network actually, not even a deep neural network. Right? That's the power of, again, this is mathematically proven. Now the big question here is, how do we determine theta 1, theta 2, theta 3, theta 4, all these weights, how do we determine? We do it again using calculus, maxima, minima, same concepts, using maxima and minima. Also, if you remember, there is a rule called chain rule of differentiation. So we apply maxima, minima concepts along with chain rule, and we come up with a concept called as a backpropagation algorithm. Backpropagation is basically simple chain rule with some basic computer science concepts. Right? Backpropagation algorithm was invented by Geoff Hinton and their students and his PhD students in the 1980s. This is one of the greatest algorithms in whole of AI. Right? I think in the course video I spent almost 1.5 hours just explaining the algorithm in depth. It's one of the great ideas of whole of AI. But I hope you got an idea, right? You can become, again, using very simple functions, you can compute very, very complex functions by just using this simple scheme of layering. This is what is called as layers. This is called the first layer, second layer. By just layering this, people assume that most likely human brain also does some complex things like this. Now, what is a deep neural network? Again, deep neural networks, the very first research paper came out in 2006, again by Geoff Hinton. The biggest problem people faced from the 1980s, look at this, backpropagation was from 1980s. From 1980s to almost 2006, lot of people came up with beautiful algorithms, but nothing worked. I'll tell you why nothing worked and how they got around it. It's almost like 25 years worth of research. What is a deep neural network? A deep neural network is nothing but a neural network. Again, this is my input. This is my first layer of neurons. Again, everything here is connected to everything. Instead of drawing the whole thing, I just drew this one yellow arrow saying that everything is connected. That's what is called as fully connected. So everything here is connected to everything here. Every input is connected to everything here. Similarly, this is also fully connected, which means this output is connected to all three of them. This output is also connected to all three of them, and so on and so forth. That's what I mean when I say fully connected. A deep neural network basically means in the 1980s, they could only train a 2-layered neural network. This is my input, my first layer, my second layer, my third layer, my fourth layer. This is a 4-layer neural network. In the 1980s, they could only train a 2-layer neural network. They tried to do 3 and 4 layer, but it was not working for multiple reasons. I'll explain what they are. Right? They just couldn't get things to work. And people like Geoff Hinton, Yann LeCun, they almost spent 25 years struggling to fix it when everybody was ignoring them. This is one of the great ideas of a great comeback in computer science, right? So deep neural network is all about increasing the number of layers. When you increase the number of layers, look at what is happening. This is computing one function. This is computing another function. On the output of these, it's computing one more function. On top of this, this is computing one more function. If you're computing more and more function composition, you get more and more powerful functions. And we can prove this also mathematically, right? I explain this intuitively in the course videos using some simple examples instead of proving it fully mathematically, because the mathematical proof is slightly complex. Okay. So from the 1980s to 2006, again, even the 2006 was the first paper that Geoff Hinton published. Actually, things started taking off only from 2012. Okay, 2012 is the watershed moment when everything started changing in deep learning. 3 major things changed. One, we started having large amounts of data. Deep neural networks require enormous amounts of data, hundreds of thousands or even millions of data points to start working with. Next, compute. In the 1980s, computers were still basic PCs. This was when your first Macintosh was built and all that, right? Today, most of deep learning is done using GPUs. GPU means graphic processing units. These are specialized, some computers have it, not all computers have it. GPUs were actually designed for gaming, but they're extremely powerful. They can do a lot of matrix operations very, 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 very fast. Again, this is some ingenious work from Andrew Ng's group at Stanford, where they were one of the first people to use GPUs for deep learning. I think around 2012-ish or 2011 if I'm not wrong. Right, so we have humongous amounts of compute power at the disposal of regular people like you and me with GPUs. Then there were very innovative algorithms that the researchers came up with. Phenomenal, like ReLU that I just explained, right? It was a major feat. Again, a bunch of other algorithms like batch normalization, a lot of hacks. Some people call them algorithms, some people call them hacks, doesn't matter. People came up with some very ingenious hacks or algorithms to make deep neural networks work even if you have 100 layers today. Today you can train deep neural networks with 100 plus layers very easily. They're extremely powerful, right? So these are the three big things that have changed from 1980s to 2006, and this has ushered in the new revolution of deep learning from 2012. Nowadays, most companies try to use deep learning for a wide spectrum of tasks. But of course, they also use classical machine learning. Okay. Now, one very popular deep neural network architecture is called convolutional neural networks. Again, convolutional neural networks, the initial idea was from the 1990s. Yann LeCun, who works as a head of Facebook AI research now, who is also a Turing Prize winner, he designed some of this during his PhD days in 1990s, but nobody took him seriously because they were not working on large problems. But what happened, very interestingly, in 2012, this is the great moment, right? People used the same ideas that Yann LeCun came up with in the 1990s. These are very ingenious ideas on image data, and they shattered they literally made all the other algorithms waste. They threw them, we threw most of these in dustbin. So today, if you have any image data, most likely you'll be using a type of convolutional neural network. Now earlier, what used to do, again, I've studied in the pre-2012 era, and I've worked on image data extensively during my master's degree days and things like that. So people, for images, what is an image? Take this image, right? An image is basically a collection of pixels. Every image has a pixel. This is a pixel, this is a second pixel. Every pixel can be represented using one red, green, blue value, if it's a color pixel. So literally, it is an image is basically a grid of numbers. Literally, it is a grid of numbers, mathematically speaking. So people from image processing and computer vision have spent almost 3 to 4 decades coming up with, now how do you featureize this data? This is humongous amount of data. So they came up with, again, in the case of our blood glucose test, right? We used height, weight, all of that stuff because the doctor said that these are relevant. So computer scientists designed handcrafted features using ideas in signal processing, image processing, and computer vision for the last 30 to 40 years. Those were what were used as features for most of, this is pre-2012, remember, this is pre-2012. This was how computer vision or image-based machine learning tasks were done. Post 2012, after 2012, the power of CNNs is they can automatically extract interesting features from the data without you having to tell them how to do it by using this operation called as convolution operation. Again, this convolution operation itself is borrowed from image processing, but you just design a network, right? You just design a convolutional neural network, it will automatically extract features, and this was godsend. Remember, in 2012, with the explosion of the internet and with the explosion of social media, there were literally billions of images on the internet. There were literally billions of images on the internet. And we didn't know whether an image contained a dog, whether an image contained a cat. We didn't know whether an image contained a medical scan. We know nothing. It was very hard to figure that out. CNNs came and changed everything in a single shot. Again, there are a bunch of CNN models. The 2012 seminal model is called AlexNet because the first author of the paper is, his first name is Alex. That's why it's called AlexNet. But there are many other models like VGG, ResNets, Inception models, etc. Again, I can't go into the depths of all of them, but we explain them in lots of detail in the course videos anyway. So again, two things helped here. Remember, so at Stanford, there is this group headed by Fifi Lee. Her group created a very large data set of millions of images called the ImageNet data set, wherein in each image they say, for each image they say what objects are there in the image. Humongous data set. See, we have large data sets. People started using GPUs or graphic processing units for compute, and the innovations from the 1990s, some of the innovation from the 1990s on the algorithms front and innovations post 2016, all of this came together in 2012 to create the AlexNet architecture. Remember, without data, there is no deep learning. Without high compute power, there is no deep learning. Without innovative algorithms, obviously there is no deep learning. So all these three things came together in 2012 and changed everything. Today, any data problem where images are involved, CNNs are the key. CNNs are, again, there are hundreds of types of CNNs. Okay, there are hundreds of types of CNNs. But this is the crux, this is the core idea here. Okay. Next came recurrent neural networks. Again, recurrent neural networks is an idea from the late 90s, I think 97 if I'm not wrong. The first paper on recurrent neural networks, how to use them, LSTMs. There are many types of recurrent neural networks like LSTMs, GRUs, etc. The first paper again came in 1990s, but nobody took notice of it. But what happened is, again, remember, from 2015 onwards or 2014, 2015 onwards, RNNs became extremely popular. I think 2014 onwards. 2015 things caught up very fast. So RNNs work very well on text, on any sequence data. Now what is a sequence? Text is also sequence, right? Text is basically a sequence of words. Word 1 followed by word 2, followed by word 3, followed by word 4, again followed by word 2. Anything that is a sequence data, like text is a sequence data. So all problems related to text, all problems, whether it is understanding text or translating text from one language to other language, all those text processing tasks can be thought of as sequence data processing. Similarly, there is other types of sequence data also. Suppose if you take stock data, take everyday stock value of some, let's say Amazon. Again, these are not Amazon stock values, but let's take them. Okay. This is, let's say on day 1, this is the stock value. Day 2, this is the stock value. Day 3, this is the stock value. Day 4, this is the stock value, so on and so forth. This is what is often referred to as a time series data. This is often referred to as time series data. But it is also a sequence of numbers. This is a sequence of words and characters. This is a sequence of numbers, right? So even for sequence of numbers like time series data, recurrent neural networks are widely used. Again, I cannot go into in-depth of RNN architecture because that's slightly more complex, right? Whether it's LSTMs or GRUs. Again, these are different types of RNNs which are very popular. Similarly, just like time series data and text data, take music. Music is also a sequence of notes. If you have ever studied music, again, I don't know much of music. Music is sequence of notes. Sa, re, ga, ma, pa, da, ni, sa, but sequence of them. That's what music is. What is speech? Speech is, again, it's a sequence of audio tones. So anywhere where you have sequence of something, whether it is sequence of words in text, sequence of numbers in stock data, sequence of syllables in speech, sequence of notes in music, for all of them from 2015 almost till 2018, almost, or let's say 2014 onwards. 2014 to 2018, RNNs were the standard technique. They were the state of the art, right? But then something changed in 2018, right? So again, this is a very interesting research from Google. So in 2018, again, I've taken this diagram from Google blog, right? Google's AI blog, okay? So Google said, okay, your RNNs are very good, but they're a little cumbersome to train and build. So they came up with a new model called as attention models. Again, this came into existence mostly in the text translation world. If you want to translate text from, let's say, from one language to other language. Okay, if you want to translate text from one language to other language, or you want to understand, for example, take this example, right? So you have one sentence here, the animal didn't cross the street because it was too tired. Okay, it's the same sentence here also. Now, what does this it refer to? Remember, what does this it refer to? Does the it refer to street? Does the it refer to street? Does the it refer to animal? Does the it refer to full stop? What does it refer to? What does this it mean here? So again, this is a task of understanding text. Translating is another task. So attention models, in a nutshell, what they say here is this. They say, when I'm looking at this word it, and when I want to understand what it means here or what it refers to, I want to pay attention to this block of words. Again, there could be some other sentences here, there could be some other sentences here. I don't want to look at that because I know this it has to refer to some word in here, right? So attention models basically say, I want to pay attention to only a few words in this window of words to understand what this it refers to. The same thing can be done in translate. Suppose if I want to translate this from English to, let's say, French, right? Suppose imagine that this was French output. To generate one output word, I need not look at all the words, but I have to look at some words more closely and some words less closely to generate the French translation or the Hindi translation from English. Right? So attention models became very popular in the 2018s. Today there is a technique called as BERT. Again, from attention came transformer models. BERT is literally one of the state-of-the-art models in text processing today. Again, we have done, I think, 4 or 5 live sessions just explaining attention models, transformers, BERT, etc. Right? Sounds good. Now there is another concept called as an autoencoder. Okay, so just like in clustering, imagine somebody just gave you the data without any class label. Suppose this is my input vector, right? This is my input vector. Suppose somebody just gave you some, let's say, somebody just gave you, let's say, images. Somebody just gave you images without telling what image is what. They just gave you a bunch of images, like in the clustering context, right? They just gave you image 1, image 2, image 3, so on and so forth. Now you want to group similar images. Now image is basically a bunch of pixels. Now what do? You take this matrix, you can convert this matrix into an array by just looking at this as, there are multiple ways of doing it, or you can just process the image matrix as is also. So what an autoencoder does is, look at this, autoencoder has 2 parts, an encoder and a decoder part. So what it tries to do is this, it inputs, this is my input image, there is a bunch of convolutional neural network connections here, right? There is a bunch of connections here. So if this is, let's say, 1000 dimensions, I'll have, let's say, this is 200 dimensions here. Here I'll have only, let's say, 50 dimensions, right? So what am I doing here? I'm trying to compress the information from 1000 dimensions to 50 dimensions. Now this 50 dimensional vector, again, all these connections here represent convolutional neural network, deep learning, all the functions that we discussed, right? So this code here, so from 1000 dimensional vector, we are now representing the image with a 50 dimensional vector. Now using this 50 dimensional vector, can I reconstruct the initial 1000 dimensional vector? Look at this. I started with the 1000 dimensional vector here. I started with the 1000 dimensional vector as my input. I shrunk it down using a bunch of functions. Again, using a bunch of functions, I shrunk it down to 50 dimensions. Now using this 50 dimensional representation, can I recreate the 1000 dimensional representation? If I can create it, what does it mean? It means this 50 dimensional vector is representing all the information that is there in this 1000 dimensional vector. Think of it as a compression strategy, right? Now comes the interesting part. Take image 1, I have a 50 dimensional vector for it. Take image 2, I have the 50 dimensional vector. Take image 3, I have the 50 dimensional vector, so on and so forth. Now I'll perform clustering in this 50 dimensional vector space. And now imagine if I get a bunch of images here, and if I get a bunch of images here. Remember, I can do clustering in any dimensional space, right? Now all these points, again, remember, instead of using the 1000 dimensional representation, I'm using the 50 dimensional because these 50 dimensions represent the crux or most of the information that is there in the 1000 dimensional data. Now by grouping together, very likely when you use autoencoders on images, you'll see that all of these are images of the same object. Let's assume these are human faces. All human faces will be clustered together. Similarly, let's assume these are all dogs, right? So by just using these 50 dimensional vectors, you can group or cluster together and recognize that all these are faces or all these are dogs. So this type of model is called as autoencoder model, right? So there is one more type of model called as generative adversarial also called as GANs. Again, I've taken this diagram from Google blog. GAN is like this. So again, you might have seen a lot of fake videos generated by AI and all of them, right? They're all generated using, again, there are tens of types of GANs. Most of them are generated using GANs. The object of GAN is as follows, right? You want to generate some data, right? So your model, using your deep learning model, you generate some data, like an image like this. Now, again, this is my generator generates the data, right? I'll have a discriminator, again, which is another deep learning model, which will say, given some, suppose if I want to create images of, let's say, $10 notes or $100 notes, right? The moment this data is given to me, look at this, the moment this $10 note is given to me, this and this image are very different. So I can say, I can differentiate or discriminate between these two images. So I'll go back to generator and say, sorry, this image that you generated is not worthwhile. It is not looking same as this. Go back and regenerate another image. Okay. So after a while, it generates a slightly better image because there is a person here. It generates a slightly better image. But then the discriminator again says, no, this is better than last time, but this is no way close to this. So it's useless. So after a lot of attempts, the generator finally generates an image which looks very, very close to the real image, very close, that the discriminator can't discriminate between the generated image and the real image, right? So that system actually looks like this. Look at this. So you give us some random input, the generator generates a sample of images, and you have some real images also. These are real images, right? The discriminator is trying to discriminate between the real image and the randomly generated image, right? If the discriminator is able to successfully discriminate, we say, generator, you're not doing a good job, please regenerate. Please try to generate images in such a way that the real images and the randomly generated images cannot be discriminated successfully by the discriminator. That is the whole idea of GANs altogether. And this is what is used a lot in generating fake videos, images, all of that stuff. Next, okay, there's this big area called as reinforcement learning. Okay, so the biggest application of reinforcement learning is playing games, robotics, and trading. Now let me give you the context. This area is mostly used to design today. Like you must have heard that Google defeated chess champions, Go champions, lot of online games champions, all of that, right? All of that is designed using reinforcement learning. It's also used extensively in robotics, right? So reinforcement learning, the concept is, this is a very nice simple diagram. Oh, I think I forgot to put the reference here. Yeah, I think it's the same reference. I'm sorry, I just Google searched and I got this. I forgot to put the reference here. Or probably it was from Wikipedia. Yes, this was from Wikipedia. I'm right, yeah. So I forgot to mention that. This is from Wikipedia. Okay. So the way it works is this. You have an agent, like somebody who is playing the game. Let's take the example of chess game, right? So you have an agent, which is nothing but somebody who is playing the game. The agent performs some action. In chess, what is an action? Moving one of your pieces. Once you perform an action, the environment changes because your opponent is also playing, right? You're playing a game, you're performing some action. Your environment also changes because the opponent is also playing the game. Now there is another module called interpreter which says, okay, the environment changed because your opponent also played the game, right? Now based on if your opponent killed you, if your opponent killed your king, it will give you a reward which is very bad. It will give you a reward which is very bad. If you killed your opponent, it will give you some reward, right? Same thing, it will repeat over many games. Again, the interpreter also, again, the state of the environment has changed. After I have played my game, the opponent has played the game, right? The environment itself has changed. That new state of the environment is sent to the agent now. Again, these terms of agent, action, reward, state, they come from robotics, right? Because robotics was one of the first areas where reinforcement learning was extensively used. I hope you got the understanding, right? This is my chess player. Action basically means a chess move. Once I make a chess move, the environment changes. The opponent also can play. And there is an interpreter here who gives me some reward. If I played well, I get reward. If I did not play well, I get some negative reward. And the environment has also changed, so I get a new state. Based on the new state, I have to decide the new action. So the agent is where we apply a lot of deep learning today. There is a whole area called deep reinforcement learning, where the objective is, can I use deep learning to make this agent very smart? Can this agent, again, think of this as a function. This agent has to compute a function, given a state, given a reward. He has to compute what is the next best action. That's all, if you think about it. He has the state and reward as inputs and action as output. Of course, this game, you could play it over many iterations and things like that. And to design this function f, typically deep learning is used, right? So again, there is a concept called as a policy. Policy basically means what action do you take when you have a state and reward in a given situation. Okay, let me show you this diagram. Again, this I've taken from this resource, QuantDare. So the way it looks is this. Look at this. This is my agent now. My agent gets the current state from the environment. I observe the current state. Using the current state, I train a deep neural network. Again, these are the parameters of my deep neural network. Based on my deep neural network, I'll decide what policy or what action should I take. Again, there could be multiple actions that I can take. I will take the action which will give me the most reward as I understand it. So I'll take that action. Based on that, the environment will change, the opponent can play. Based on that, I get my reward now. Again, I'll keep playing this. Over a period of time, my deep neural network will become good enough, very good enough actually, to tell me what is the right action at any time step, right? Again, this has become very powerful with games like even, I don't know if some of you play Dota and other games. It's become very popular and people are able to play. I mean, there are, again, Google has this team called DeepMind that is based out of London, a very cool research center which work extensively in deep reinforcement learning. And they have been beating every major game. Some games that even people thought were impossible for computers to beat humans. Again, this is also very useful in robotics. Look at this, in robotics or even in self-driving cars. You can think of your self-driving car as a robotic car, right? In your self-driving car, what happens? Or in your robotics, your agent is your robot. Okay, suppose you want to go from one position P1 to another position to P2 while avoiding all these obstacles. Let's assume all these are obstacles. You want to go from P1 to P2, right? So it starts going, it will get stuck there. Then it will come back. It will try, so it has to find a way to go from P1 to P2 while avoiding obstacles. So my robot now is the agent. My environment is the physical environment in which I'm operating in. If I get stuck, I get a negative reward. If I keep moving forward, I get a positive reward. At any point, I can observe and I can take an action. My action can be in a robotic system. My action can be turn right, go a few steps forward. All of those are actions, right? So in both games and robotics, reinforcement learning is extremely powerful concept and extremely widely used, right? So yeah, I think I was just on time. So somebody is asking about deep reinforcement learning. So good question. So let me answer some of these questions here that we have in the chat window. I think I've just finished on time, but I'll spend 10 more minutes answering a few questions, right? Okay, let me answer whatever is there right now because these people have asked for a while. So do you plan to introduce reinforcement learning in applied AI course? We were planning to do a couple of live sessions to give an introduction to the topic. But the reason we avoided it till now is because there are fewer roles in the industry around deep reinforcement learning, right? Especially in India, because most companies in India work on other areas like text, images, etc. Because again, deep reinforcement learning, if you have to teach it in depth, it's almost like 50 hours. We didn't want to overwhelm people by so much content, while the number of positions are fewer. Because in India, we don't have too many robotics companies. That's one biggest problem, right? If you are in China, probably yes, deep reinforcement learning could be extremely powerful because they have a huge manufacturing sector. We had to make a trade-off there. But we'll probably do a couple of live sessions on reinforcement learning so that you get the basic idea of what it is, right? So will this recording be available on YouTube later? Yes, it will be available for all to see. Add suggestions on Facebook. Which algorithms do Amazon and Google use? Very good question. So they use as of 2016, 2017, most of them were using GBDTs and random forests, mostly GBDTs actually, for their ad recommendation. But slowly they're all moving towards multi-layered perceptrons and deep learning models because they are performing slightly better than GBDTs. But almost for a decade, I've seen these algorithms at Yahoo, Google, Facebook, Amazon. I've read tons of these because I worked on online advertising for Yahoo Labs and for Amazon. People started off with logistic regression, then people went on to GBDTs, random forests extensively. Now I've heard, because I'm no more working there, I've heard that they have also moved some of those modules to deep learning stuff, right? Somebody saying, could you do a live session on debugging? Yes. So in the live sessions that we're going to conduct starting tomorrow, we will be covering debugging, how to resolve error messages and all of that in lots of detail, right? So don't worry about that. Okay, so how quantum computing is used in AI, machine learning and DL? Yes. Again, please don't fall for hype words right now. Quantum computing is a very important, ingenious idea, but we are still not there. It is still a research topic right now. I really wish quantum computers become a reality. Today we are not at a stage where quantum computers are widely available, or I hope Google, IBM, Microsoft crack the quantum computer problem and make it available to all of us on their compute platforms. Because if you do that, the whole of, just like the way deep learning transformed machine learning and AI, quantum computing will transform it by one more leap. If you have good quantum computers available on the cloud, hopefully in the next 5 to 10 years, the whole of computing will change. Forget about machine learning AI. Machine learning AI will change enormously, but whole of computing itself will change, right? So if you can solve a problem using decision trees, why to perform kernelization? Good question. So yeah, so remember that all these concepts came up at different times. Kernel trick SVMs were very popular in the late 90s, early 2000s. They were used extensively, right? Then in the early 2000s, your random forest and GBDTs became very, very popular. So over a period of time, techniques evolve. There are some models for which a decision tree or a random forest might be too complex. Again, it is hard to predict beforehand which model will perform well on which data set. You'll have to experiment multiple. You can give some good hints and directions, but you can't be always certain about it. It is better if you try multiple models. There are some data sets on which simple kernelization using a random basis, using a radial basis function, RBF kernel, works much better than even decision trees, random forests. So that depends on the data set very much, right? Make a live session to deploy ML/DL models on Android. Again, Rakesh, the only reason I wanted to do it because I read a lot of TensorFlow Lite and TensorFlow JS stuff. The only reason that we stopped for it was primarily because many of our students may not know Android development, right? They may not know how to write code in the Android Studio, all of that stuff. Teaching all of that is it's too time taking, right? But if you want to learn, just shoot an email and we'll try and share resources with you. Actually, just look at TensorFlow Lite. Google has terrific tutorials on TensorFlow Lite, which you can deploy on both Android and iPhone. Because I actually read the Google documentation and learned about it myself, right? So, okay, Maruti, I think I just answered your question, right? That in the future live sessions, we're going to do that for sure, right? Okay, sounds good, folks. Somebody says, suggest me a data set for social network analysis. Let me show you. Kaggle, I think social networks. I think, I think there is a case study that we did, which is part of our course using Facebook data. Let me look it up. It's just a Google search away, guys. Many of these things are just a Google search away. Getting started undirected graphs. Okay, this is some notebook. I want data set. Facebook data. Exploratory data analysis. No. 1 second. There is a competition, a Facebook recruiting competition. Yes. So look at this. In this, Facebook actually gives anonymized data. This is an old data set, but that's okay. So this is a very good data set wherein they give you social networking data from Facebook, Facebook actually conducted some recruitment competition to hire data scientists based on winners in this for their Menlo Park office, right? So this is one data set. Again, we could find it in like what, 10 minutes, less than 10 minutes. Even if you're slightly slow at searching, any data set you want, just type Kaggle or data set this, search for about half an hour, 1 hour, you will easily find it, right? So that's what I would recommend. Okay, folks, I think that's all I had. Thank you all for joining in, and see you again soon. Again, we'll be doing some of the live sessions that I promised you, the daily live sessions. Some of the early live sessions on Python, we'll do it for everyone on YouTube. So tomorrow's live from 6 p.m. to 8 p.m. I'll make an announcement by late night today or early morning tomorrow about what that live session will be. Because everyday live session is like, I'll have to prepare everyday notes. I take about 7 to 8 hours to prepare for a 2-hour live session. So I'll keep announcing this on YouTube. Some of them will be for everyone. Whichever do not require course videos, I'll do it for everyone. Whichever requires course students, whichever requires course videos, we'll do it only for registered students. Somebody is asking, what is the 10,000 feet view mean? If you're flying in an airplane at 10,000 feet, how do you see the world, right? You see the world as big chunks. You don't see the small roads and all that. You see the big picture of things, right? So that's what the 10,000 feet view actually means. Very commonly used, right? So sounds good, folks. See you again. Thank you very much for joining in. And again, please stay safe. Very, very importantly, please stay safe, okay? And try to build on your skills. I know some of you are panicking about the lockdown, the pandemic, and probably, we don't know yet, probably the recession that would come later. Please focus on skills. I have been through one recession just when I graduated. I know it. People who build skills, in the long term, you will succeed, okay? Please don't look at your career as the next 6 months, next 1 year. Try to look at it from a longer lens, because most of you will work for the next 30 to 40 years. At least I plan to work for the next 35, 40 years myself. So we have 3 to 4 decades of career ahead of us, mostly a couple of more recessions or even a depression in the next 4 decades. We don't know how many more pandemics, hopefully none, but we have to prepare for the long term, not for the short term, right? Okay, folks, see you. Bye-bye.